Hey there, ever have one of those days where you feel like you're putting in a ton of effort just spinning your wheels, but only a little bit of it is actually pushing things forward? Well, believe it or not, there's a perfect piece of math that describes that exact feeling. Today, we're going to break down vector projections and see how they help us find the truly useful part of any effort.
Seriously, think about it for a second. Whether it's cramming for an exam, trying to move a couch, or working on some huge project, not all of the energy you put in goes directly to the goal, right? So the big question becomes, how do we figure out which part of our effort is the part that really counts? And this right here is the classic example that nails it. Picture yourself pulling a heavy box with a rope. You're probably pulling up at an angle, not perfectly straight. So yeah, part of your force is pulling the box forward. That's the good stuff. But another part is just pulling the box up, basically fighting against gravity. That part is wasted. Vector projection is the amazing tool that lets us perfectly separate the useful forward pull from that wasted upward pull. Okay, so to really get this, we need a strong visual. And honestly, the best way to think about a vector projection is to imagine one vector casting a shadow on another one. Just hold that idea in your head. A shadow. This, this is the fundamental question that vector projection is designed to answer. If you've got your force and you've got the direction you want to go, the projection tells you precisely how much of that force is actually working in that specific direction. It's really just asking, how much of me is pointing the right way? So here's the more official definition. A vector projection is what you get when you break a vector down into two separate pieces. One piece is perpendicular to the direction you care about. That's the wasted upward pull in our box example. The other piece is parallel. That's the useful part pulling it forward. And that parallel piece, that is the vector projection. It's the shadow itself. And this is a super important point because it's an easy place to get tripped up. There are actually two flavors of projection. Over on the left, you've got the scalar projection. That's just a number. It's the length of the shadow. It answers the question, how much? Then on the right, you have the vector projection. This is the shadow itself. It's a full-on vector with both a length and a direction. It answers, what is the actual effective force? Okay, I know what you're probably thinking. Uh-oh, here comes the scary formula. But hang on, we're not just going to drop it on you. We're going to build it together, step by step, so it actually makes sense. Turns out, any vector projection is really just made of two super simple ingredients. First, we have to figure out the length of the shadow. That's our scalar projection. Then, once we have that length, we just need to tell it which way to point. We give it a direction. That's it, length and direction. So, ingredient number one, the length. This comes from some pretty basic high school trig. Yeah, SOHCAHTOA? If you think of your force vector as the hypotenuse of a right triangle, then the shadow it casts, the adjacent side, is just the magnitude of that vector times the cosine of the angle. Simple as that. Now for ingredient number two, direction. We need something that points the right way but doesn't mess with the length we just found. And for that, we use a nifty little thing called a unit vector. You just take the vector you're projecting onto, like the ground in our box example, and you divide it by its own length. What you're left with is a tiny vector that's exactly 1 unit long, pointing in the perfect direction. It's pure direction. And now we just put them together. You take the length we found, our scalar projection, and you multiply it by the direction we found, our unit vector. And boom, you get a brand new vector that represents the shadow with exactly the right length and exactly the right direction. That, my friends, is our vector projection. Theory is cool and all, but let's see how this thing actually works with a real problem. This is where it all starts to click. All right, check out this situation. You've got a father pulling his daughter on a sled. He's pulling with 100 pounds of force. But the rope isn't perfectly flat, right? It's making a 30-degree angle with the hill. So the question is, how much of that 100 pounds is actually pulling the sled forward? And this is where you have to read carefully. The question asks for the effective force. It's asking how much, which means it just wants a magnitude, a number. It's not asking for the full force vector. And that tells us we don't even need the whole formula. We just need ingredient number one, the scalar projection, the length of the shadow. So all we have to do is plug our numbers into that simple trig formula from before. 100 pounds times the cosine of 30 degrees. And what do you get? 86.6 pounds. So out of the full 100 pounds of force the dad is using, only 86.6 pounds are actually doing the work of pulling the sled. See? That's the power of projections.
All right, we have covered a lot of ground here, from shadows to sleds, so let's just boil it all down to the most important things to take away from all this.
If you only remember one thing, remember this. A vector projection is just a shadow. The scalar projection is the shadow's length. That's just a number. The vector projection is the shadow itself. That's a full vector. And, most importantly, it's an incredibly powerful tool for finding the useful bit of any force that isn't pointing in exactly the right direction. So I'll leave you with this thought. The next time you see someone pulling a rolling suitcase at the airport, or you watch a flag flapping in the wind, stop and think about it. What are the vectors at play? What's the useful part of that force? What are all the unseen forces acting at an angle all around you every single day? Thanks for listening.